Okay, and we're live. Hello, Andrew. How are you? Long time no see.
Yes, a long, long time, and I'm trying to work out. Yeah, we're looking at probably more than 10 years, actually.
Yeah, I was trying to recollect, but so I left Microsoft, or at least the compiler, at the end of 2009.
Right.
And I have been in Seattle till 2015, so we might have, seen each other maybe. But, it's been at least 10, maybe 15 years. So
That's right. That's right. Exactly. A lot
you
has
look great.
changed.
Lots of change, but you haven't. You look great. You are still, you haven't aged. So I don't know.
I don't know, a lot more white hair.
Yeah, they say it's wisdom. So I just back from GTC, the
hmm
Nvidia
hmm
GPU, what is that, technology conference,
Yes, yes, yes.
and I thought about you a lot, right? Because we saw, well, first of all, a lot of talks about AI, AI agents,
hmm
slice and dice, possible verticals, which is, I don't know, maybe we can talk about that later.
hmm
And then, Jensen talked about the GPUs, the future, and with a lot of nice graphs about ISO power performance and ISO power, a lot of ISO power. But then, at the end, if you see from one chip to the next, they consume more power, right? I mean,
Absolutely. That's right.
so, and then I thought, oh boy, I need to talk with this about this with Andrew, because it's like, are we going to hit a wall? I
hmm
mean, and also about your physics aware
hmm
architecture. I'm very curious about that. And I don't know, where do you want to start?
Um, I think I mean, it'd probably be good just to have a sort of general discussion of history of computation, actually, and then from there try and work out where it goes, right? And each of us have a different perspective because of just where we were in the industry, and I think that would be probably a really good place to start, actually. Um,
Let's do that.
yeah. So, I mean, if we go back to, von Neumann is to blame for everything that we have. Uh, he made a
Probably.
set of decisions, right, about 70 years ago, and they weren't bad decisions. They were good decisions. It showed that we could. He made a set of decisions of how. I mean, he didn't do the computer architecture. Other people created that first architectural manual that he's known for, but he made some decisions on how we should move forward in computation, and it's done really well. I mean, we basically we have all different architectures, all different things, but if we come down to it, it all comes down to von Neumann's original design. And but now, we've 70 years on, every so often there has to be a change, and because we've done everything that we can explore in a certain area. We've used so many mathematicians, we've used so many great designs, and we come to the end of a way of looking at computation. And you see that with everything, with modern cars. We come to the end of internal combustion engines. They're fantastic. They've lasted 150 years. I mean, we've got beautiful engines, and they're about the most efficient we've ever produced. But they come to the end of what we can do with them. We can't drive them further. We can't improve them any more than we've got. And
Let
so you
me,
see, yeah.
yeah, sorry if I interrupt you.
Yeah, yeah, please, please. Yeah.
There is one starting point, or one. So when I was working in Microsoft for the compiler for ARM, and you were working for ARM, and I remember this ARM, I don't know, executive founder, someone very old. I forgot the name. Right, that around.
Mike Muller, Mike Muller.
I don't know really. I read something, or you might actually have told me this. I don't know. So he was doing an interview, and the journalist was asking something like, "Hey, how do you feel? Because lots has changed since you started doing ARM, I don't know, 20, 30 years ago, right? And now." And the guy said, "No. the usual computer science problems,
Hmm.
data structures, Q, just the scale is different, the transistors are
Yes.
smaller, the scale. So how do you feel about that? Is it
Yeah,
changing now?
I think very much we have, the scaling is amazing now. I mean, in some ways, the majority of people are probably looking at a different scale of the problem, right? I borrowed an analogy from somebody which said, we started off in the 50s with a little hut. We then moved to a small village of a design. Then we moved to a small town. Then we moved to a city. Then we moved to a large city, of complexity. I mean, and then we moved to metropolises, super cities. Then we moved to designing at the country level, and then the continent level, and then the planet level. I mean, and we've exceeded the planet now. We're doing exoplanets where it's hard to find a planet big enough. Maybe I did a joke recently that we're more at the small galaxy level or something like that in complexity. And that's how chips are. I mean, we're designing at such an amazing size of systems. And there's this concept of dark silicon, which is quite nice in a planet sense because the sun can only heat up one side of the planet, the other side is cold, right? So as
Yeah.
dark silicon, is quite a good analogy in the fact that you can see that you've got a power problem, a distribution problem, and we can only highlight some of the transistors at any point in time. Yeah.
Okay, so you were talking about the history of computations and hardware, and then you mentioned car, and so about the car, maybe this is a tangent, but you said we cannot improve them more, but isn't that more an economic problem? Meaning, for who produces car? At the end, cars serve a purpose to bring you from A to B,
Right,
and
right,
they do
right.
that, right? So
Yes.
if you want to sell more cars every year or every 5 years, you want someone buy a new car, you need to be more appealing, more nice, more sexy, more
Right,
I
right,
don't know
right.
more what, but anyway, so uh, computation, what's changing? The problems that we are solving might be the same, but the scale is different. Power is a big factor, right? So will we hit a wall? Like, we need GPUs bigger to compute, build bigger AI models, and then at some point, what do? We fight wars to build the biggest plants, or we nuclear plants. I mean, where are we going with power? Do you have an idea?
With power, right. So computation can be solved at different levels. So I have like an analogy with the huts going to an exoplanet, scale of complexity. With power, it's a more complicated piece because there are many levels, right? So okay, we can increase computation by adding more power stations. That's
Yeah.
a simple way of thinking about it, right? Or we can think of computation as increasing efficiency. So you're looking at doing more balancing of compute, memory, and communication. You're balancing all of those pieces to get the perfect piece of technology that can run at a certain power envelope, right? We can then think of, efficiency of dealing with the hardware. So DeepSeek is a fantastic example where they really looked at the hardware to see where, how do we map computation really well to the hardware as opposed to just using the hardware generically. And so you can increase it that way, and that's increasing efficiency by just understanding the computational engines you have. Um, then we can miniaturize the logic, right? We can keep miniaturizing the logic and add specialization. So, where we understand this is the algorithm we want to adopt, and this is the specialization that we have to execute that algorithm, then there's the what I would call the general problem of memory movement being actually the biggest problem in computation, as opposed, I think computation itself has gone off over the hill with the capability. It's just feeding that computation is actually the biggest issue we have. Maybe we change it that way. You concentrate, and you see a lot of these new chips have huge caches and huge shorter distances between main memory and computation, and a lot of work being done in that area. And then finally, you've got what I would call the logic substrate, which is the right core level where you have a level above which is digital, and underneath you have an amazing world of complexity that you can add into the logic. And we'll probably talk about that later on. You're literally re-looking at that sort of abstract layer of binary digital activity. And so and I see it like that, really. But the crudest way is just adding power stations, and resources, and you just throw lots more power stations to get more compute. As opposed to the AI systems, they seem to be, we add a new lane in the freeway or the motorway or whatever, and it just consumes it. It seems to consume it. I suspect there's going to be a slowing down of the rate of returns, because as you add more data, as you add more complexity, there's a complexity level of the AI systems on their own where you get to a point when they're too complex, and the information coming back doesn't really make huge amounts of sense, right? I suspect there's a sort of, there's a point when there's a slowing down of returns. But I'm not super expert in that area, but I have it's more of a feel that the bigger you end up going, well, actually we're getting more confused information rather than better information.
And so where does a physics-aware architecture fit in all of this?
Right. So physics-aware architectures. So it's a sort of more general term. I mean, where the company I'm in is being more specific to it, but it's a more general term in the fact that if we look at most of the core physics equations that run everything, they're reversible. And we've gone for it's go back a level, it's go up a level a bit. So today's digital systems are what I call suboptimal minimalism. So what we do is we make the logic as minimum as possible to allow us to scale to do all sorts of things. But it's very, very simple. We have zeros and ones, and it's what I call suboptimal minimalism. It's about as basic as you can get to do a lot of computation, right? And the question is, if we add a little bit of complexity, can we get to optimal complexity? Is there a level of adding complexity underneath that gets us away from the suboptimal and gets us nearer to the optimal as adding a little bit more complexity at the lowest level of computation, right?
What do you mean? So having machine instructions that are a little bit more complex, or something else?
There are many levels.
Okay.
And the transistor, does some channeling, and it does some movement of information. And in the end, we group a whole load of transistors. They do an add instruction. They do all of this other stuff. That's the suboptimal minimalism. We brought it down to such a low level, and we're really good at it. I mean, we produce lots of silicon using this type of technology. The question is if we add a little bit more complexity into that minimalism, can we effectively do more or create more efficiency, right? And this goes back to the physics-aware architectures, right? So in physics, there's a bag of really interesting tricks they have, in what they can do in the physics level. And the question is, can we bring that bag of tricks and up the complexity of the minimalism that we've normally done, and expose a little bit more of that interesting level of where voltages, electrons, and capacitance and induction all goes, and try and bring up the level of the lowest level. And by doing that, we can engage in much more efficient systems. We can deal with a lot more complicated problems. We can, there's a whole load of different goodness there. So that's the sort of general scope. And then going back to my earlier comment, if you look at the sort of core physics equations of the world, they are reversible. We can go forward and we can go backwards, right? They've got a fundamental core characteristic that we don't do in electrical engineering, and we don't do in computation normally. And Feynman and von Neumann actually both were aware of this reversibility concept. Feynman declared that we know about reversible computing, we know about reversibility, but we also know it's extremely hard to do. And we would only do it if we're being forced to go down that route, because we know it's complex. It's a complicated route to try and get that type of physics going at an electrical engineering point of view. And von Neumann.
Give me an example.
Yeah.
Give me an example. You got me curious. Using physics tricks to make computation a little bit more complex, reversible.
Right.
Give me an example. How could we use that?
Right. So one of the interesting tricks is this concept that actually, where does heat go? What produces heat in computation? Let's go down to some fundamental levels of thermodynamics and all the rest. And if you look at modern circuitry, you're charging things and then you're discharging them, right? And in the laws of conservation of energy, when you charge something and discharge, when you discharge, where does the energy go? Well, the energy goes to heat. I mean, you literally produce heat in discharging energy. So each transistor and each sort of capacitance and all the systems, as we erase information in the system, each one is producing a tiny bit of heat, tiny bit, nearly negligible bit of heat. But as you add scale and as you add frequency, you're starting to build this bigger heat production system. In fact, you're really building a heater in this sort of let's call it a micro world. And if we understand the physics of this, then maybe what we do is we try and reduce or control how we erase information in a computer, because that's the core for the heat production. Heat production causes us to limit our frequencies. It causes us to put massive amounts of money into cooling. It causes us the difficulties in scaling, because you don't want to concentrate a lot of heat production in one place, because it just gets too hot. There's a whole load of problems produced by heat. So it's just taking this one concept of sort of controlling erasing of information, you start building an interesting idea of how you change computation, because you don't want to erase information, you just want to control the erasing of information. You want to control it very carefully, so you limit the amount of heat being produced. And that isn't like a perpetual motion machine. You can't reduce it completely, but you can, because you understand the problem, you can start doing clever things about where that energy and discharge goes, right? So instead of allowing it just freedom to discharge, you start going, well, can I use that energy somewhere else? Can I put it back into the system? What can I do with that energy, right? So so then you've got this controlling of discharge. So what do you do? Well, there are techniques to recapture energy and flow it back into a circuit. So we understand all of that. Are these techniques been a major focus on the industry? No. I mean, we've been concentrating perfectly. I mean, 99% or even higher of the industry has been concentrating on just getting frequency and scaling done. But very little has been done on going, well, how do we really control the heat production in a system? So that's really an interesting idea of whether we build sorry cycles in the system instead of having just a system that goes in a line. We put heat in, we put energy in, we do computation, it produces heat out, and hopefully it produces a result. So that's our normal computational system. So if we start going, okay, you put energy in, especially initially, and then you control the heat coming out, and then somehow, so here's some magic. Yeah, somehow we grab the energy and re-put it into the circuit. So you're building a cycle as opposed to
Electrical energy
an
or
electrical cycle. Yes.
okay.
Right.
So at that level, at the transistor level, let's say, you
At the
recapture
transistor
it.
level. Right. So and this is complicated. I'm not going to say this is an easy thing to do, but it's this ability to think of circuits as energy cycles is that allows us to do all sorts of really unusual things. So it's take away the detail. So it's take away the complexity of just trying to do that.
Yeah.
And look at the benefits. Well, the benefits are, well, we dramatically reduce the heat of the circuits. So we dramatically get rid of a lot of the waste of energy just driving circuits. So it's take a battery, you make it last much longer on a battery, for instance. You know, that's the sort of behavioral aspect. At the data center, you know, you're looking at sort of removing sort of cooling from the data center. I mean, at the moment, I think two-thirds of all the energy in a data center is dedicated to cooling.
Wow, I didn't know that. It's a huge number.
And then if you add the latest technology being announced by all these wonderful companies, you know, you're seeing it going to 3/3 because most of the problems are going to be heat, trying to get rid of all the heat.
So how much circuitry or space in the chip do you need to add? So let me go back a moment. Can we do a metaphor? Can we? Is this similar to my hybrid car? So when I hit the brakes or when I go downhill, it recapture a little bit of energy.
Yes,
like I don't know.
Yes.
Okay.
Yes,
so and you do that like a circuit. So let's say we have an adder. 32-bit adder. 32 lines come in for A, 32 lines from B, and then there's something in the middle, and then 32 lines come out for the response. So you're saying if inside this other black box or there is another line coming out, a power, or maybe more than one, a power, saving line or so that goes back into somewhere. Is it an accurate picture?
Yes, it's an accurate picture. I mean, the thing is, it's thinking of it as a cycle and a process, right? It's the control of the system rather than letting it go wild by just producing heat, right? It's a controlling element, and you're quite right. Regenerative brakes are examples where it captures some of the energy, but maybe not all. A pendulum is a beautiful example, right? So you set a pendulum going,
Yeah.
and it goes forward and it goes backwards, right? And it slowly loses energy. It's slowly, but it's a very efficient slowing down. And with our circuitry, you would have to, you take the pendulum and you bring it back to its original point and then let it go again, because you have to put a little bit of energy into the system. It's not a perfect system. It's one where you got to continuously. But once you've got the pendulum working, it works really all the time, right? It's constant with very little energy being added into the pendulum, because the initial energy required goes in, and then you just keep adding a little bit. And the trick here is to build a cycle as opposed to building an open circuit. So an open circuit would be you will really, as I described, you put energy in, you allow heat to come out, and then hopefully you get a result. There's always this hope that you can get these results, and this is allowing more of the physics and the physics principles to try and change the way we do circuitry. This is really where the physics or where architectures come in, because you go, well, we've got these ideas here in the physics world, is see if we can bring them into the electrical world to see if we can do it. And is it easy? As Feynman said, we don't do this because we want to. We do this because we have forced to do it, because we're coming to the end of our traditional electrical engineering flow, and that's where this comes from. And it's exciting. I mean, this is sort of a different way of approaching things that we haven't really looked at for 70 years. This is quite a long time and in some ways you're fighting education, you're fighting training, you're fighting industries that have been done this, right? It's a very different way of mindset of thinking.
So can we go a little bit more in details of this?
Yeah.
Because when you say you need to control the system, you mentioned cycle.
Yes.
So what does it mean? So are there changes only at or transistor level? Are we talking about changes in the architecture or
So
at
so
macro
so
architecture level? So if I
so
take
there are
my
a
book,
number of pieces like
digital, if I take my
yeah.
book, digital the design, will
Yeah,
that
so
still
so so
be the same design for adders, multipliers, and such, or
sure.
small changes or big changes?
So, so, so first of all, the most important thing is we've got a huge amount of software out there that believes in a certain world, right?
Yeah.
So it's go top to bottom, right? And so really, because I use the term logic substrate to mean everything above works like a normal system, right? It does the calculations, it does everything it appears behaviorally like normal logic. An add does an add, a multiply does a multiply, a subtract does a subtract, right? And software is quite happy with that. It doesn't want to see anything strange, right? Underneath the substrate, as in underneath that sort of what I would call that abstract level, we can start playing, and in thermodynamics is playing with what is called Maxwell demons, but in realistic terms it is about just seeing where energy goes and controlling the erasure of information and flowing it back. So on one side you have a little more complicated clocks. So traditionally we have clocks that do square waves and cycles. We may adopt a different type of clocking completely for this type of
Oh.
logic. So that's one level. Another level would be to have a way of instead of discharging the energy, putting the energy back into the circuit. So we have to have some piece of technology to do that. And then we've got another piece of logic, which is, I mentioned reversibility at the beginning. In reversibility, the main use of reversibility is to allow the information to stay long enough instead of discarding it and producing heat like we do traditionally in circuits, you keep it long enough so that that energy can be recaptured and put back into the circuit. So you're dealing with multiple components all having to work together. You can't do one without the other. It's you're
Okay.
trying to build what's another analogy is take the internal combustion engine, which I mentioned before. You have two cycles. You have an expansion cycle and a retraction cycle, and likewise you try and do that in electronic circuits. You have an expansion cycle that creates the result, and then you have a contraction cycle which allows the energy to momentum to go back, and then you expand again, right? So you're trying to build this sort of flowing cycle into the system, and this is unusual, but above the logic substrate you want to be the same. I mean, we could expose more of the underlying knowledge
Yeah, yeah.
underneath, but
Yeah.
above we try and be the same as everyone else. And you mentioned area, so everything has to have a compromise, right? Every piece of technology. So with suboptimal minimalism, your area is very small actually, because you're reducing it down to the bare minimum of what needs to be done for computation. For this technology, we will need more area, because area is what as you add complexity, you add an area overhead into the system. And the question we have now is, how much area is
Yeah.
required? How much extra area? How much extra area does can the world allow from a manufacturing point of view before this doesn't work, right? And this is the equations we're working with. I mean, we're as a company, I'm talking about my company as opposed to a general theory. We're playing with what you would call the efficiency complexity graph, where if we add this amount of complexity, how much area increase, and can we allow that area to increase, right? And is it 10,000 times, in which case you get this remarkably efficient system, but it causes you huge amounts of area. So the trick here is to keep the areas reduced down to an overhead that is reasonable, right? And yeah, I mean, this is both exciting, but also complex to explain where we are, and we're at an early stage of just taking this one concept and bringing it out. I mean, we are an early stage startup, but trying to take a set of theories that have got different pieces and actually really implement it on real silicon, doing real stuff, right?
Well,
So
an early stage startup is always a very fun place to be.
right,
I suspect that maybe, all of a sudden in, I don't know, 2, 3, 4, 5 years, or more or less, you might be at center of attention because we hit the wall, power
right,
wall, or transistor scale wall, and some, and
right.
all of a sudden you will have billions of funding. But okay, without violating, intellectual property or anything for your company, can we talk about a real example of, I don't know, some very small circuitry like an adder, or something, and see, because I might have read
Yeah.
something about reversible computing months ago
Yes,
when
yes, yes, yes. So there are different levels. So the trick here is on the word reversibility and reversible computing. And there are different concepts here. And there is, true reversibility is a mathematically perfect system. So true reversibility has, I've got is do an add instruction. You have A and B, and you produce a result. And the important thing in reversibility is that you also have A and B that there's an ability to go back to the A and B, right? That's true reversibility from a mathematical point of view, right? You know, But when we're dealing with energy, in some ways, we're less concerned. Well, especially at the beginning, because we're more interested in the heat and the efficiency side of things. So we do. I tried to invent a term which is pseudo reversibility or something. There's a term where really what we're caring about is not the mathematical part of reversibility, but the control of the energy part of the reversibility. Because it's the discharge that we're caring about, not
Heat,
necessarily the mathematical part of the reversibility idea.
can we call it heat first reversibility?
That's right. That's right. Or energy first. Yeah, exactly.
Energy
And
first.
so that's, and can we do true reversibility? Absolutely. We can go all the way to the mathematical term, but I don't think, this would involve, as you well know, in the compiler world, this would involve quite a lot of new compiler concepts, and the repercussions of true reversibility in the mathematical sense is interesting, but it may not need, we may not need that at these initial points to get what we want, which is the energy savings at this point. But maybe in 5-10 years we start adding the mathematical parts of it. We've got all the pieces to do the mathematical parts as well.
Okay, but if we take the adder, okay, 32-bit adder.
Yes.
So let's say there will be some different clock. There will be some kind of wire or circuitry at the transistor level that will capture some energy. But at microarchitecture level, you have 32 wires coming in, 32 wires coming in on the other side, 32 wires going out. There will be some control, right?
Yes.
I don't remember much about digital design, but there will be like the clock. There will be like I don't know, maybe negate the first argument or negate the second. The overflow. There will be some other wires. In your scenario, in this energy first reversibility, is there any other wire that will come out or in at this microarchitecture level?
So I think the simple answer is we're calculating all of this. I mean, you're really in a real time. This is we're talking at the edge of the technology that we're working on, right? So at the moment we are calculating this, and we're trying to work out the best answer for that. And as I said, if we do the pseudo reversibility, we're really only interested in the energy levels that we can recapture. If we're doing full mathematical reversibility, I think there's a whole load of papers on, how many wires and how many calculations you can do. I mean, the interesting thing in reversibility is when you scale up to more complicated sort of multi-combinational logic, you're doing the adder and the multiplier. But the truly interesting thing is how do you build up, in a mathematical sense, a more complex circuit, and what does reversibility mean in that complex circuit, right? Does it mean more wires? Absolutely. Can I give you an exact number? Not at this point, because we're not really. That's not our focus is on the energy and heat our output first.
But can you tell me something? I mean, this is getting interesting, but I know there is IP wall somewhere. So let's assume that the audience knows about modern CPU architecture, right? So we have instructions that get decoded. They are, I don't know. Let's talk about a RISC core, right? All the basic instructions, ALU, memory transfers. Well, when you say this applies to something more complex, are we talking about what are we talking about? So do we need a more complex chip to really save power, or can we apply these techniques to
yes, so there are different levels. So there is doing what is called the logic cell level, which is the fundamental building blocks that how electrical engineers build up systems. Believe it or not, they don't invent everything. They use these little modular components, and then they wire them up. And and we can hide the abstract level. We can hide our logic substrate underneath and provide the normal, the cell library type stuff from an electrical engineering point of view. When we come to processors and things like that, so MIT showed a set of reversible compute processors in the late 90s. They did everything the we could do, but they didn't do the energy recycling. They made the energy recycling off chip. And so they did the reversible logic, you know, in silicon, but they did all the power stuff up outside. And the trick here is we're actually bringing the power stuff, which I think is actually the more important part, onto
inside.
the chip. And so by trying to get everything, so where, you know, what's been done is the power stuff has been done, the logic has been done, but they've never been all done on the same, on doing it all at the same time. And that's really what we're attempting to start to do, is build everything into a single piece of silicon. And then once you've got that, then we could go to a processor, we could go to a GPU, we could expand out, but first you've got to get the fundamentals right. And you know, and is it easy? No, you know, it's actually a really hard thing even to get the fundamentals right. But once you get the fundamentals stabilized and we get our equations settled down on, you know, how much capacitance, how much inductance, how much, you know, flow of energy we can do, and what are the limitations of frequencies and size and area, then we can start moving to more fundamental pieces. You know, I mean, our hope is to move very quickly because the logic, the digital logic's already there in some ways.
Yeah.
We just need to build the fundamental blocks, and then we can move quickly forward. And but you know, it's easier said just getting the fundamental blocks getting to work. You know, you know, this is you know, this will involve quite a lot of experiments to you know, to see how it works and to see what the characteristics are. I mean, it'll be different to, our characteristics are going to be different, you know, no matter what, and they will be surprising in some ways and, you know, odd in others, right? You know,
Yeah.
we may be so deeply surprised, oh, we can do that, right? You know, that we can do that type of stuff. So you know, you're talking at a very early stage in our progress. You know, our excitement will be, you know, the first type of silicon, you know, and then we can start moving from there.
So what's the roadmap, if you have one, if you can share it?
Um, we start off with the fundamentals, and then we grow to product as fast as we can. So the roadmap is relatively simple. We think we know what the product side we need to do. The question is, does the technology, can we bring the technology along with the roadmap, right? So that's, you know, we can have these ideas, but we need the technology to run parallel to being able to produce the product, right? But we have a fairly clear view of where we want to go, and we'll test that out with various people to see, well, is this interesting? Is this something we should do? Because in some ways we have both a technology and a product. So a potential. So a technology is universally providing to everyone. You know, a product would be to solve a particular problem
But
in.
when you say product, you mean you will build silicon, you will compete with companies that make chips, you compete with Intel, Nvidia,
Yeah,
or
we
you
can
will
go
provide a service?
in at this point in time, we can go in any direction we want to go, right? And you know, we could produce an end product like a chip that fits into a system and can be used with hopefully high efficiency, low heat, all of these things. So you can scale up to huge numbers or whatever. So on that side, you know, it could be a product. You know, are we you know, and how good that product is determines how far we can scale up even further beyond that, right? So I mean, this the idea we see from a technology point of view is the whole world will adopt this technology in the end. You know, it's not a this you know, if you look at where the semiconductor industry is, we, you know, there will be a forcing function to go here. It's not just us developing the technology, not us just doing this. There will be a forcing function to get here, because we want more efficiency, we want scaling, we don't want heat, we don't want cooling.
Yeah.
But there are fundamental things that will force the industry down this route.
Okay.
So, but hopefully we'll be slightly ahead. That's our goal, right? Is to be slightly ahead of everyone else, right? So,
Well, given the size and the markets of the chip makers nowadays, they probably will buy you with a ton of money if they as soon as they hit the power wall or something. But
yes.
yeah, I mean,
I
you
mean,
made me
take
curious.
out actually. I mean,
Yeah,
that's just taking your point there. Take out all the details. This is a good thing for a company to be looking at. And there's an issue with timing, right? There's a timing issue, and there's being too early, where a company looks at an area too early, and then becomes relevant. That people realize it's relevant. 20 years later or 10 years later. I've been in those companies. I've been in the startups where we designed one of the first tablet computers. But tablet computers really didn't take off another 20 years. so
wow.
I've been at the early stages, right? And then there's been too late, and too late's okay, but you end up with a technology where the rest of the industry has moved forward. And I don't want to name names, but I always felt Intel's Titanium
Yeah,
processor was ahead of its time, but it ended up in a world where the traditional technology had done so well that it was difficult to compete against it. And so there's a sort of nice window where you arrive a little bit earlier than is required. You get all the pieces ready to do that, and then then the world realizes the world needs this type of technology, and I think we are just in that nice we're just in that nice window where we're a little bit early, but the industry is going to hit this problem dead on fairly soon. And that's a timing issue, and all startups have to deal with this issue, whether you're dealing with AI, whether you're dealing with a new data center chip or whatever. There's always this worry, of timing, and it's one of the most complex things in the industry.
it is. Timing is crucial, and having been a few years in Microsoft Windows Phone, I know about timing. Unfortunate timing. Well, you made me a lot curious. Is there anywhere where I can find maybe those MIT work that you mentioned?
Yeah.
So,
Look up a person called Michael Frank, and you'll be able to find all the pieces from here. And he works for VR Computing, and there's a whole set of. I don't want to do the physics. This physics person said this physics person said that. So I've tried to avoid the going down into particular physicists. But there's quite a lot. There's been quite a lot of thought here, and it's been going. Michael Frank has been working on this for 30 years, to work out this, and he's thought about the architecture. He's thought about the energy flow. He's thought about all these different things for 30 years. And you just look him up. He's done talks at Stanford University, on YouTube, and all of these other things. So he's very learned in this area.
interesting. Yeah, I'm curious because you mentioned this ability to recapture power or energy at a little bit higher or more complex scale than a simple adder, and so now I need to think about that. Will I find something online on the state of the art, or is this something that you guys are
There
working
are
on?
little bits. VR Computing, the company I'm in, we have most of those people. The most of the people that work on this are actually in the company itself, and so it's a fairly small community because the reason it's a fairly small community is traditional technology is done so well. I mean, there's no doubt that von Neumann made the right decision 70 odd years ago, and all the others have been absolutely correct. I mean, it's not that they've done the wrong thing. The problem is, we're coming to an end of the runway, and the end of the runway in multiple areas. So I think there's an announcement of 2 nanometer chips coming out this year, or the end of this year is the hope, right? And then there's talk about ASML's 1 nanometer technology, right? And a 1 nanometer, I think, what is that? I'm trying to work out the Armstrongs of that, but
10, I guess.
yeah,
10
it's called it
Armstrong is
10
one
or
nanometer.
14 or something. It's called it 10 Armstrongs. A silicon molecule or atom is roughly 2 Armstrongs.
Wow. We are
So
there, another couple
you know,
of
it
generations.
doesn't take a huge amount of understanding to realize that we're coming to the end, and our runway may not end at it may be not at 2 Armstrongs, but at anywhere between where we are today and 2. So we're looking at maybe 8, maybe the end of where we can go with this type of technology. And then what do we do? Do we change the manufacturing equation? How do we do that? Our thoughts are you actually change how we deal with computation and heat, because we believe that's the biggest problem that we have in circuitry. And actually, heat has been the biggest problem for the last 10, 15 years. And actually, we've been trying to pretend to ignore it and just keep miniaturizing. But really, when it comes down to it, the heat is the biggest problem we have in computation. And it's limiting our frequencies, it's limiting everything. I always remember going to the Pentium 4 presentation by Intel. I mean, I sat there, I went there, and I was just amazed by this, because the Pentium 4 was state-of-the-art processor at the time, right? And they go, well, they go, performance equals architecture times manufacturing was what they were explaining in this presentation, right? And they go, by concentrating on manufacturing, we can do much better on performance than we can on architecture. And they go, and we've made this faster and better and more powerful because we've concentrated on manufacturing. They then said, well, the big problem was the heat. So we used to use just standard fans, but the fans we needed to bring in aeronautical engineers to design the new fans, because the heat was too much, right? So they designed a fan. The aeronautical engineers designed this fan that would go on top of the processor to cool it down, right? And then they go, well, and then we had the problem that the fan was too heavy. So the fan was too heavy being put on top of the processor, which bent the boards down. So the circuit boards were being bent down because they only were, I don't know what that stage were. I guess there were four layers or 2 layers. They weren't the big layers. They were trying to optimize those. So they then had to build a spring system to keep the boards flat so that it didn't strain the boards, right? And you go, wow, so this is why heat is such a problem. It isn't just heat, it is the cooling systems, it is the secondary effects, there's everything else that has to occur. And I sat there going, I'd never thought weight of processors was a problem in the industry, but weight plus the cooling systems plus all of that, I then realized, that was becoming a major issue.
So when
And
you
I
solve, yeah,
Mhm. Yeah.
when you solve the heat problem, or where you mitigate the heat problem, does it mean
Right.
that you can build bigger chips and faster frequencies?
So there are multiple levels we can if you solve the heat problem, and as I said, I used the 2/5 example in a data center. Imagine having access to 2/5 more energy to run a data center. You immediately start being able to scale more, right? So there's a scaling point on the chip itself. Possibly, what we did. So we hit Dennard scaling problems, where miniaturization wasn't increasing the performance particularly more. There wasn't huge dramatic increasements of performance as we scaled down the transistors. So what we did was we started putting more computational elements onto the silicon. So you started putting 2 processors and 4 processors, and you started seeing scale by parallelism, really. And there, that was our way of mitigating this. Our single thread performance was going down, but we could scale it out. But with the miniaturization, we have a huge landscape to play with. It's like a painting frame, and we can choose to put the same computational elements and just repeat it, because that's what we've done up to now, because it's easier for us to copy blocks than to use it as a complete canvas, because it's complicated as a complete canvas. If we can do sort of computational blocks like chiplets and things like that, verifiable modules, then we can just combine them into the silicon. If you add the reversible computing side of the world, what you see is a decrease, hopefully a dramatic decrease in energy, a dramatic decrease in heat, but a slightly bigger blocks. So we fit into this traditional flow, but they will, there has to be a compromise somewhere, and as I said, we're trying to work out what that area requirements are going to be, but that would be where we could do. Would it mean larger chips? I'm not sure. That's
Slightly.
I mean, there'll be larger bits for our logic, but maybe slightly. But I'm not sure. That's not something. I'm not sure that's something. More efficient chips, yeah, absolutely. Less heat being produced, as I said. But I'm not sure it will mean larger chips. I'm not sure larger chips are a good thing from a yield point of view. You're wanting more efficiency rather than larger chips.
Okay.
I'm thinking, it's not a question I've thought about very much, but the concern, the bigger the chips, your yield goes down, because everything, at least most of it, has to work. I mean, there are ways of getting around errors and trying to use as much as the chip as possible, even if it's got errors in manufacturing. But that tends to be quite low yield, high-end chips.
Okay, I don't know if you need to go. We are close to 1 hour recording, and I was curious because you mentioned frequency, you mentioned this different clocking system. So I don't know if you can elaborate on that. I don't know if you can say.
Right. It's a clocking system. So at the moment, the best and easiest way to describe our clocking system is we're very cruel and harsh to our transistors. And we treat
up,
them,
down,
we abuse,
up, down.
yeah, we abuse our transistors like the question is, by changing the clocking system, can we be nice to them? Can we use them to their full efficiency? And that's where the clocking stuff comes in. And so you go, well, abusing the chip, abusing them has been fine, but again, is produces more heat. You're literally pushing them to their limits. You're also probably reducing their life cycles, the lifetime of being used.
Probably.
And so as you have more hot and cold all the time, you're reducing the lifetime of these technologies.
So are we talking
So
about slower and smoother transitions instead of
yes,
up?
yeah, exactly. I mean, you're just being nicer to them. You're gently shifting them as opposed to bang, 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 right? On the transistors, and so
Would that reduce the frequency or the instructions per second?
hmm?
Will that
Sorry.
reduce the frequency, the actual frequency, or the actual number of instructions per second?
Um, I don't think so. It's a good question. I think we've still got to work out those equations. As I said, there's quite a complicated equations we're sort of trying to work out. It shouldn't be that noticeable. I mean, maybe a little bit, but it's more to do with you know, it's more to do with efficiency more than computation. As I said, I think computation has gone over the hill. I think we've got far better computation than we can even feed. So to me, we've got lots and lots of
That is
margin to
correct.
play with. Yeah, we've got lots of margin to play with. I mean, it's feeding them, it's putting them, it's moving the data into these computational layers, and it's taking them back out. You know, I've done this odd analogy where you go, well, let's add some two numbers. So the processor requests a number, and the request goes through a field, into a tunnel, out of the tunnel, over a fence, down another tunnel, another field, gets to the memory. The memory provides this piece of information, and it goes all the way back, goes through the tunnel, over the fence,
Well, the
through
memory,
along the field, and then it
maybe,
puts
yeah,
that
yeah,
number
it was
there, and
back.
then it repeats it for the next number because you need to add two numbers, and then it does the calculation, and then the result has to be then put through the tunnel, over the fence, through the tunnel again, over the fence, back into memory. That's to do just a simple computation takes so much effort, and that's why in memory computation is becoming so interesting, because the normal computation cycles take so long to go out and then back in, that if you can do the in-memory computation like Heinlex and all of these other memory companies, that's a huge advantage, because you're not moving everything through these physical PHYs, which is the interfaces between memory and digital logic. And that's an interesting area on its own. I mean, that's a sort of architectural side. Yeah, it's a different area, but it's interesting.
Because
Yeah.
let's remind for people that are watching that computation and memory, so CPU and memories, they are built with different electronic, different materials and different processes, and they are very different, and they stand apart. And
Mhm.
while a processor can do maybe 4 or 5 instructions per nanosecond, memory takes 20, 30, 40 nanoseconds to go and access something. And actually, memory is a block device. You don't get
Yes.
1 byte of
Yes.
bit. You get usually,
That's
I don't know,
right.
64 bytes or whatever. And
Yes.
that's why we built all these complex architectures of caches.
Yes.
Well, you have a small, very fast cache, L1, and then you have a slightly, much bigger, slower L2, L3, it's inside the chip, outside the chip, and and the prediction mechanism to feed those caches. So when you
Right.
do a computation, you get data from the caches and not from the memory. But
Yes.
then you have a lot of cores with their own caches and
That's
synchronization mechanism, which is super complex,
that's right.
just to hide the fact that memories are slow. But
That's
so
right.
to we go back to your point. So we are saying that frequencies and your strange clock, your nicer clock, less abusive clock, will contribute to drastically reduce heat generation, and at the end will not drastically change the compute power of the chip,
That's
because
right. That's exactly. I mean, that's the hope, right? We have to do some experiments. We have to fine tune the equations. We have to prove end to end that the whole thing works. And then once we prove everything works, then we start optimizing. we start optimizing the
When you say
process.
equations, it seems to me that so you are not yet at the simulating
Well, no,
phase.
we are there. We are there. The thing is more on the optimization side of the world.
Okay, okay, okay.
It's okay. We've got these numbers. Okay, what can we do here? What can we do with this switch? What can we do with this transistor? How do we change the capacitance and the induction
Yeah.
here? It's really at a low level, detailed, low level set of decisions. And so in VIA we have physicists here, we have analog engineers here, and we got digital engineers here. So it's a combination of three totally different disciplines trying to communicate with each other to try and get this to work. And when we have to learn a common set of terminology and understanding between all three. And that's the trick, and that's the physics awareness comes from the physicists. The analog engineers play with actually the analog engineers. So I came from a digital world. The analog engineers have a huge amount. So in the digital world, we really have only two colors. Like zero
Black
and
and white.
one. We paint all our pictures with 0 and 1, and with the analog engineers, they just have this amazing collection of colors that they can play with. I mean, it's just an unusual experience, and they can do
Wow.
things in different dimensions that no digital people are just not used to, right?
Yeah.
Because our world is a bit like if you lived in a two-dimensional world and three-dimensional people turned up, it's things would emerge that you can't explain from your two-dimensional world, right? And the analog people are fascinating. I mean, to me, but they need to live they need to create things that produce digital outcomes, because otherwise the two-dimensional world does not understand the analog stuff, right? And that's the critical key here.
You must be having a lot of fun over there.
Oh yes, yes, yes. A lot of learning, right? And trying to experiment with something very new. And new is exciting but hard at the same time, right? Because you're having to make decisions, and you go, well, is this the right decision? Because no one's written the book on how to make this decision. You're
You
not
are writing the book
because
as you
we're
go.
writing the book as we're going along. That's right. That's exactly right.
Yeah,
And
you are into the unknown. So
right.
wow, it must be cool. And well, I hope to have you here again when you go live, maybe with the product or with some
Oh,
cool
so
announcements.
so that's a good thing. There's probably some interesting things to talk about in about, what I said, about 3 or 4 months time.
Oh,
And
that's wonderful.
we'll if we have another of these sessions, 3 or 4 months time, I'll be able to say a little bit more about where we are and where we've progressed, and a bit more tangible things.
Excellent.
Yeah.
In the meantime, well, it's been a pleasure. I will always follow you on LinkedIn or wherever you. Do you write in other places, or it's okay to follow
No,
you on LinkedIn?
LinkedIn is my favorite. I found, I could go in many places, but I decided I got all these requests by LinkedIn early on, and I go, well, I'll either do LinkedIn properly or I won't, and I
Yeah.
decided to use LinkedIn as my main way of communication. And yeah, there are other tools, but they just, I find LinkedIn is just a natural one, and I hopefully put out things that are interesting as opposed to just sort of, I see a lot of marketing, which is fine, and marketing
Yeah.
departments should be doing
Yeah.
that. But I try and put out things that are slightly different to a traditional marketing type thing, and some of it may be a bit strange, some of it goes, why is he talking about this? All of that, but I try and do something which is different to just normal sort of pieces. And I may be wrong, and I'm quite happy for people to say, well, actually, if you think like this, then that's a different perspective. I really love that, actually.
Oh, I love the perspective of going back to hardware, going back to physics,
Yes.
and especially with this power war coming at us in.
Yes. Yes.
Because it's coming, right? If we are at 1 or 2 or 10 or 20 Armstrong, and the atoms are 2 Armstrongs,
Yes.
as you said, we might be 8, 9. I mean, we have at most one other iteration, or maybe 2. 20, 10. I mean, so the wall is there.
Yes,
2 to 5 years.
Yes, that's right. And then we have to think 3D, right? And then
Yeah.
what's the biggest problem with 3D? Well, is thermal meltdowns of the chips, because
Yeah.
if we use traditional technology, we're putting all that heat right into the middle of a cube as opposed to a two-dimensional image. And so you quickly realize that it then falls into our world again, because our world is trying to remove the heat system, trying to reduce how much heat is being produced. And so the 3D world, is going to
I'm sure it will have a little bit of runway, because they will find a way of putting cool, liquid inside the chip. There
Yes,
might be
right,
another
Yes.
iteration or 2 will be done like that. But how much can you do with that?
That's right. That's right. And and that's very expensive and very complex just to do
It
that.
is. It is.
And if we can avoid producing the heat in the first place, then maybe that's the better route, and then we can have solid blocks of computation,
Yeah.
as opposed to lots of liquid going through. I'm seeing a lot of complexity there on the 3D side, but
Yes,
also
I agree.
we want to produce true 3D chips as opposed to just the layered 3D. So there's this idea that you just put a whole load of 2D chips on top of each other. That's the sort of crude form of 3D. The next, I can see a future 3D where they actually do use the diagonals and start, actually building real 3D chips. We have CAD tools that can cope with layouts of true 3D systems and the ability to build in 3D. And that's and that'd be probably like a 3D printer type way of building these more exotic ways of doing 3D.
Excellent. Well, people, stay tuned for the next generation
Yes.
physics-aware hardware. And thank you, Andrew. Thank you very much for your time. And I will ping you, for sure in 3-4 months, and we will see what you have.
Yeah. 3 or 4 months is about right. I mean that will be an interesting time to talk. Yeah.
Excellent. See you then, and thank you very much again for your time.
Okay.
See you, man.
Bye.
Bye.